So in this class, I'm going to do a revision of sampling distributions. You should have already seen this before, but just for completeness sake, we will review them in quick time. So the first thing is you have a sample x1, x2, xn from the population. So let's say it's IID from a population, IID sample from a population with distribution x, let's say. So sample, population X. So now what we do is, this is the data we have about the population. So now one of the few things one can do with the sample is that you can try to understand some descriptive things about the population. So the first statistic that you do is, it's called the sample mean. So let's call the sample mean. So here, what sample mean is what? X bar. So X bar is just 1 over n summation I equal to 1 to n xi. The other distribution is other statistic that one can immediately get from the sample, which is called the sample variance. And that's just, we'll call it as S square, or some people call it S square n, some people just call it S squared, and that's just 1 over n minus 1, the sum from I equal to 1 to n xi minus x bar, the whole square. So here, this sample variance has two standard things. One is that you take the sample, subtract the mean, the whole square, that's like the variance, sort of. Then we normalize it by n minus 1. This is because in statistics we prefer an unbiased estimator. So that we will come to a little later if we have time. But you can also use n. If you use n, it's not an unbiased estimator, but it's a fairly good estimator of the sample variance as well, of the true variance as well. So one of the key things in linear models is we'll encounter such statistics again and again, which look like x bar and look like s squared. So various as we go along in this course. So one of the questions one tries to understand is just one second. One question to understand is that what is the distributions of these sampling quantities? So I'll just say, what are the distributions of x bar and s squared? So typically one cannot say anything because x can be very general. Then one cannot understand what x bar and s squared look like in terms of its laws. One can simulate and check, but otherwise to write an explicit form is quite hard. But there is a nice answer when the underlying population is normal. So I'll write this down. So there is a nice answer when xx is normally distributed, let's say with parameter mu and variance sigma squared, then one can answer, one can understand, let's say one can quantify the distribution of x bar and s squared. So let's try and answer this question in this setting, at least the first part for x bar. So let's just check that. So let me come back here. So now what I'll do is I'll assume each of the xi's are normal with mean mu and variance sigma squared. I'll try to find out the distribution of x bar. So that should be easy, right? So for example, so now we know, first thing is, suppose each xi, x1, x2, all the way till xn are all distributed as normal with mean mu and variance sigma squared. then we know, and they're independent, so they're all independent normals, then we know that the sum of normals remains normal if they're independent, and the means just scale up appropriately, and the variance adds up in squares, right? So therefore, this will imply that 1 x bar, which is just 1 over n, sum from I equal to 1 to n of xi. So this can be thought of as what? You can think of it as summing up I equal to 1 to n of xi divided by n, right? So each of these people is a scaled normal, and I'm summing up normals. So just the variance will add up and the means will add up. The means unfortunately gets scaled by n by this, and the variance gets scaled by n squared. So let's do that observation. So first observation is that each xi by n is distributed as normal. So the mean scales by n and the variance scales by n squared, right? That's how the normal random variables properties are, right? So it's a fact, right? It's a fact, we know this. So this is true for every I, 1 less than equal to I less than equal to n. So now, if you look at x bar, so therefore, if you look at x bar will be distributed as normal. Now I'm summing up n of these guys. Each of these guys is mean mu over n. So I'll just get normal with normal distributed. Let me call this parameter as 1 and then mean as parameter 2. So where the mean parameter is just going to be what? Mu by n plus mu by n plus mu by n times, because I have n people right here, right? So it'll be exactly equal to mu, right? And the variance will also add up. So sigma squared by n squared plus sigma squared by n squared all the way to sigma squared by n squared, I'll get sigma squared by n. Right? So therefore, we find that the distribution of x bar, that's easy to see, it's just normal with mean mu and variance sigma squared by n. So that's an interesting fact immediately. So moment your underlying population is normal, then the sample mean is also normally distributed with mean mu, and kind of funky is that the variance reduces by n, right? So that sort of adds to this idea that the sample mean is a good estimator of the true mean. So let's make a small remark. So observe the mean of x bar is equal to mu, and the variance of x bar is sigma squared by n. So therefore, as n gets larger, the variance of x bar gets smaller, I'll just say gets closer to 0, which will imply that x bar is a good estimate for the true mean, which is, that's one observation in this. But this fact is anyway typically true. If you have an independent population, the mean stays the same and variance stays like sigma squared by n. This is just regardless of the fact that it's normal or otherwise. Normal population means that distribution remains normal as well. Very good. So it's an independent fact. So it's like I'll just put a star here. This is regardless of whatever distribution x has. The mean of x bar is mu, and the variance of x bar is sigma squared by n. Of course, now the question still remains: how do you understand the distribution of s squared? Okay, I will not prove this in this class. I will state a result, but before that, I would like to sort of just digress a little bit and discuss two distributions. That way, it's clear to all of you what is going on. So now, let me try to motivate you how to find the distribution of thing. So for this, we will need to understand what the chi-square distribution is. So I'll just call it chi-square distribution. So here the idea is that you must know how to transform a random variable and compute its distribution. So let's just do one simple calculation. So just to motivate why I'm doing this is the following. See, I have s squared looks like, okay, this is like some sort of normal, okay, and I'm adding a square to it. So I'm adding sums of normal squares, and I'm normalizing it. So I have to understand how a square of a normal behaves. So let me do the calculation first, okay, and that's where chi-square comes in. So here, so let's say x was distributed as, let's do a simple one. Let's say normal with mean 0 and variance 1. So let's do calculation of this. And then I'm trying to understand, let's say I take z, or let's say I take y equal to x squared. Okay, you set y equal to x squared, and then I want to find the distribution of y. Right? So how do I do this now? So what you do is you do it in 2 steps. So the first thing you do is you find the distribution function of y. So you find the distribution function of y. So here I know that I had to find probability that y is less than equal to 1. Right? I had to find what that is. Right? So now, if you look at it, that's the same as the chance that x squared is less than equal to y. Now clearly this side is a positive quantity. So if this is negative, this probability is 0. So so let's say y is in R. You want to find this, right? You want to know what this is. So first step you identify is that if y is less than 0, this will imply that the chance that y less than equal to y is same as chance that x squared less than equal to y, but x squared is non-negative, so this is going to be equal to 0. So that's the first thing you draw. Now if y is positive or non-negative, then what does this imply? This implies that the chance that y less than equal to y, that's the same as the chance that x squared less than equal to y. And that's the same as, take this down. I'll make it a little bit down here so that it's clear. This. Let me erase this a little bit here. That's the same as the chance that minus root y is less than equal to x is less than equal to root y. Right? That's just we know exactly what it looks like. Right? So now that's going to be just the chance that minus root y to plus root y of the normal density, which is e to the minus x squared by 2 over root 2 pi dx. That's exactly what it's going to be. Right? So here I've used the fact that x is normal 0, 1. Right? Normal 0, 1. So I'll make it all in one line so it's clear. Very cool. Right? So now once I have this, then I know that this I can calculate, right? So how do I calculate this? So it's an even function. So the integral on the negative side and the positive side is the same. So this will just become twice 0 to root y e to the minus x squared by 2 over root 2 pi dx. And that's going to be equal to, so now here you do a use substitution. You set z equal to x squared. So it means dz is 2x dx. Yeah. So this will become twice 0 to x, 0 to y, sorry, 0 to y, because z is root y. Z is x squared, so x is root z. So you get 0 to y. And then here you'll have z to the minus half, so you'll have a 2 as well, so you'll have a 1 over 2 z to the minus half e to the minus z by 2. So make z like this, so it's easier. So it's easy to identify like this, and I have a dz. This is what I'll have, and I have a root 2 pi. Very good. So that becomes the half cancels off, so I get 1 over root 2 pi, 0 to y, and I have z to the minus half e to the minus z by 2, the whole dz. So this is what probability y less than or equal to y is going to look like when y is non-negative. Right? So that's equation 2. So we can solve the integral, but we'll leave it like this. There's no need to do this. The reason why I'm saying is that now from equations 1 and 2, since the distribution function looks continuous and differentiable, you can differentiate it using the fundamental theorem of calculus. So this will imply from 1 and 2 the simple exercise to show that the density of y, okay, so first of all, it's 0 if y is less than or equal to 0. That's easy because the derivative of 0 function is 0 at the top, right? And then for y positive, what will we get? So we will get 1 over root 2 pi. That's standard, right? That's going to be like this, right? And then I'll have z to the minus half, which is just y to the minus half. I'll differentiate in y, and then I'll have e to the minus y by 2. Right? That will be the density function for y. I may have, yeah, that's correct. So that's what I have. Very good. So that's the density function for y, and this is called, y is said to have a distribution called chi-squared with degree freedom 1. So I'll explain what this degree freedom 1 in the next class. It's called chi-squared 1. We'll stop with this right now. We'll come back and do it in the next class, how to find the sample distribution of S, how to find distribution of S squared, which is one of the key sample distributions.